Hello and welcome to the first video on calculus differentiation. So before I go into differentiation proper, I feel like I need to explain the concept of limits because I feel many students do not understand the concept of limits well enough, and what results is they rely on memorization for the entire topic of differentiation and integration. And I feel that is quite sad because differentiation and integration is actually a very beautiful concept. And if you understand limits, you come to appreciate the genius behind this idea. So to help you understand the concept of limits, I have 4 checkpoints on the right-hand side of the screen. And I believe by going through these 4 points, you have a very good understanding, a picture in your head of what limits are and what do they have to do with differentiation. Now, I can't possibly go through all 4 points in one video. That will make a very, very long video, which nobody will want to watch. So you'll expect a few videos just to cover the topic of limits. So without further ado, let's get to know limits a bit better today. And on the first page of the notes, you see 2 guys with long hair. Who are they? You can make a smart guess. They probably have something to do with differentiation and integration. And why do they have long hair? It kind of shows which era they come from. I will give these 2 guys a proper introduction, but for now, just know that they are important people you might have to know. And let's go on to the next slide, the next page. And on the next page, here's a phrase that you might have heard before. Depending on how far along you are in class for differentiation, you might have heard your teacher mention this before. And the phrase goes like this: taking limits as h approaches 0. Now, I don't know about you, but when I first heard this phrase, the questions in my head were these. What are limits? Why are you taking limits? Is it something physical? Is it like a candy bar that you can take? Why are you taking limits? Is it delicious? Nobody knows, right? And approaches 0. Why are you approaching 0? 0 is not a stranger. You know him very well. Why not just go to 0 or be at 0? What's wrong with 0? Okay? And these are the answers I would like to answer. These are the questions I'd like to answer today. Okay? And to answer them, let's look at simple number patterns. Let's start with this simple one. We have a pattern that goes on. Pattern number 1 is just 1. Pattern number 2 is 1 plus 1. Pattern number 3 is 1 plus 1 plus 1. And if you continue this pattern infinitely many times, you will arrive at some sort of t infinity, where you have 1 plus 1 plus 1 plus 1 plus 1 plus 1, all the way on and on forever. And the question that I would like to pose is this: what is the value of t infinity? Okay, to answer that, maybe we should look at the simple examples first of t1, t2, and t3. Now, if you look at t1, it is just 1, because we only have 1 plus itself, or rather just 1 itself is 1. Now, t2 is 1 plus 1. We know that. That's 2. And 1 plus 1 plus 1 is 3. So if you reason this out yourself, you would think that, hey, if I keep adding 1s and I don't stop adding 1s, isn't that going to be infinity? And you're right? If you talk about that, you're right. Because if you just keep adding and adding, of course we will reach infinity. So I kind of agree with this statement in red, right? Yeah, so in this case, what I will say instead is, as the number of 1s approach infinity, then the sum approaches infinity. The sum means that if we add up all the 1s, right? The sum is going to approach infinity. Maybe thinking like, oh, well, why don't you just say the number of 1s is infinite and the sum is infinity? Why do you have to use the word approach? Okay, so I think I will use another example to explain that. Now, here's another pattern, kind of similar, but the terms are different. Now, in pattern number 1, we have half. In pattern number 2, we have half plus a quarter. In pattern number 3, we have half plus a quarter plus an 8. So pattern number 4 would be half plus a quarter plus an 8 plus 1 over 16. Yeah, hopefully you can catch that so you know what the pattern is about. Okay, suppose we do the same thing as the first one. We let this pattern continue on infinitely many times, okay, such that we have a t infinity. What would be the sum of all these terms if we keep adding on forever and ever? Yeah, and you would think that, hey, isn't this the same as the last question? Right? This is going to go to infinity, of course, right? And I will say that, in this case, I do not agree. And you'd be like, why? But if we never stop adding things, then doesn't that go to infinity? So I'd like to explain this with a visual example of a frog. Okay, let's take a look at this frog over here. This frog is on a number line. Its current position is 0, right? Its goal is to reach 1, right? It wants to get to 1. Okay, but it's a bit special, this frog, and you can see over here, right? This frog always jumps half the remaining distance. Okay, half the remaining distance, which if you look at its current position 0 and it wants to get to 1, the remaining distance is 1. And since it jumps half the distance, it will jump half over here. So let me put that down, that is half, and let me move this frog to half because that's where it lands after the first jump. Now, after the first jump, can you see the remaining distance is half? From 0.5 to 1, that is also a half. So now, in the second jump, it will jump half of a half, which will be 1/4. Right, half of a half is a quarter. Okay, and then we'll move this frog to its new position over here, which is now 3/4, which means the remaining distance is 1/4. And it will jump half of that distance, half of 1/4, which means you'll jump 1/8. Okay, and then I'm going to move the frog over here. And you might be able to guess that the next jump is going to be 1/16. The jump after that will be 1/32, 1/64, 1/128, 1/256, so on and so forth. Now, hopefully I have answered your question in your head that why does it not reach infinity? Okay, this is a question. Will it reach infinity? Right? Hopefully you can answer that yourself and see that no, this frog is going to get closer and closer to 1. In fact, it will never go past 1. So therefore, it will not reach infinity. Okay? But the more important question to ask is that where will this frog end up if it jumps infinitely many times? Right? And I think a lot of students will say that, hey, the frog will reach 1. But if you think about it carefully, does it actually reach 1? Okay, I'm going to use a green dot to represent the frog. Say it's here. Say it's really, really close to 1. Would it jump directly to 1? No, right? It will jump half of that distance, right? It brings it really, really close to 1. But from there, does it actually jump to 1? No, it will jump half of that distance again. And from there, it will jump half the distance, half the distance, half the distance. It will never reach 1. Yeah, it will never reach 1 if you think about it carefully. And that is where we actually say this, okay? Hopefully, you should be able to associate this frog with this pattern over here, right? Because when we talk about t infinity, where we're adding half plus a quarter plus an 8, we're actually adding up all the distances jumped by the frog as it reaches very, very close to 1. Okay, so we say, let me remove the blue blocks. There you go. As the number of terms approach infinity, what do I mean by terms? The terms are all the fractions over here. These are terms. Right? As the number of terms approaches infinity, the sum, right, which means if I add up all the distances jumped by the frog, it approaches 1. It's not equals to 1. I'm sorry that I wrote equal here, but what I really mean to say is it approaches 1. And by approaching 1, I'm saying the frog will never reach 1, although it is very, very close. Yeah, so that is the idea of approaching. Right? You get really, really close to somewhere, but you are never actually reaching the destination. Okay, I'm sure you can understand why the frog approaches 1. It will never be at 1. Now, why do we say approach infinity? because infinity is also some place that we will never get to, right? In fact, infinity is not a number. It is a concept or something that is always, that's so big, you can't get there. Okay, let me explain with an example. Say if you think that infinity is a big number, maybe 10 million, then I'll say to you, why don't you just add one more to 10 million, right? And you'd be like, hey, yeah, I can add 1 to 10 million, and that is 10 million and 1. Then you say, okay, let infinity be 10 million and 1. Then I'll say, why don't you just add one more? And you get 10 million and 2. And you go like, okay, right, let's make infinity 10 million and 2. Then of course I'll say again, why don't you add 1? By now you should be really frustrated. You'd be like, okay, let infinity be 10 million plus 10 million and 3. And you can see this goes on forever, right? Infinity is something you will never reach, because if you have a big number, you can just add 1, you can just add 1, you can just add 1. And it's a number that you will never reach. It's a number that nobody knows what it is, right? So we can only approach infinity. We don't know what it is. We can only approach it. Yeah. So I come to the end of the video. Hopefully I've answered the first checkpoint on the checklist, and that is adding infinite numbers of terms does not get you to infinity. And also I've explained the concept of approaching. Yes. So thank you for watching. In the next video, I would like to talk more about limits and what part do they play in differentiation. So until the next video, catch you on the flip flop.